And we're live from downtown Mill Bay. Perfect. Perfect. I have a quibble, but yeah, oh, actually, outer ring. Perfect. 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 There's one problem with this one. Inner ring's good. In fact, inner ring's awesome. The other class, about half the people made the mistake of not pairing the innermost ring, and you guys all made that. But what's wrong with this outer ring? How many spots are there for electrons? Four. And so there's an empty spot, but these are all full. I've done the toilet stall theory of electrons. Yeah. So if you're walking in and you see there's a spot farther away from everybody else, you don't have to sit next to other people going to the bathroom. You will take that spot. So they don't pair up until they have to. One way to do that is when you're going around. So this one has 6, is go around, and I usually pick the points of a compass and just do them one at a time in like clockwise or counterclockwise. As long as you're consistent, it doesn't matter. 1, 2, 3, 4, 5, 6. And if you do that, you will always spread them out until you have to pair, and it'll always work. Other than that, it was good. It would have been perfectly fine last year. And that was good. So now we're going to count the valence electrons. So how many valence electrons does sulfur have? 6. So, attendance first. Aiden? No, Aiden. Arnie?
Yep.
Bowen?
He was here.
Oh, he went to the washroom. Graham?
Yep.
Grayson?
Here.
Jamie?
Yeah.
Layla?
Yep.
Liam?
Here.
Mari? Mari? No. Matthew?
Yeah.
Miyabi? Nick?
Yeah.
Noah?
Here.
Rachel?
Yeah.
Rose? Violet? Yuma? Did I do this last day? Asking you the number of valence electrons? Put away your laptop, please. In your bag. Away. We don't need a laptop out. Okay. Randomly then. Number of valence electrons in oxygen, please. Liam.
6. Wait, no, not 6. Wait, yes, 6.
Yeah, always be confident. 6, and then never change your mind. If you do that, you can become president someday. Being right has never always helped, but being confident definitely does. Oxygen has 6. Does anybody know the really fast way, just by looking at the periodic table, how to tell the number of valence electrons? Oxygen, how many, yes?
So if it's below, so the markers you have to worry about is like 2, 10, and then 18. And
2, 8, and then 18.
2, 10, like is after 10.
Oh, I see what you're doing, yeah.
Yeah. If it's above 10 with minus 18, below 18, you just minus the number by 10.
You're doing a lot of math. That also works. But if you have the periodic table in front of you, and I say oxygen, how can you get it really fast? Yeah. Well, column is 16, but you can just count. 1, 2, 3, 4, 5, 6. And that works because it mimics the structure. There's 2 in the first shell, electrons, and then 6 in the next one. So if I said boron, it would be 1, 2, 3. You just count along. So if I ask for fluorine, say, from Violet, 7. Silicon, Noah, 4. Chlorine from Jamie, 7. And now the piece de resistance, bromine from Matthew. No. Not 17.
Mine's 7.
It's 7. The reason that it's 7 is that when we get down to here, we count like this. 1, 2, skip a few, 3, 4, 5, 6, 7. So I cheated on that because I always rely on someone getting that first one wrong. And when this is filled up, they're no longer valence electrons. They go away. For those who are up at the board last day, it's because these are the same energy level. Technically speaking, these are a lower energy level. What? Why do you stop that? Ah. Duh. Scroll. Yeah. And practically speaking, all it really means is once they're full, you can skip all of them. They go away, they lower their energy, and they're no longer part of the valence shell. So fluorine, chlorine, bromine, and iodine, and technically astatine, it's in brackets, it doesn't really exist naturally, all have 7 valence electrons, which is why they're all in the same family, which is why they all have very similar properties. Now, if you were in here, and I said scandium, you would say it's got 3 valence electrons. You would include it until it's full. But we're not really going to do that. We're mostly going to give you stuff that's in here or in here. Yes?
How would you clarify the difference between scandium and gallium, or like 1 for each of the other 3?
They actually have similar properties in some ways because of that, because they both have 3 valence electrons. Now, they're not the same because these electrons are in the p orbital, and these electrons, p orbital and s orbital, and this is the d orbital and the s orbital, so they actually change their shape, but we don't consider shape in science 10. So, but in many ways, gallium forms +3, scandium forms +3. Gallium likes to form +1, scandium likes to form +1. They both have similar properties. So, yeah, they are more alike than you would expect from 2 random elements just because they both have 3 valence electrons. So, we did the Bohr for sulfur, and I'll draw that in a second just to make sure people who are not here have it. But the Lewis diagram, we only do valence electrons. So the Lewis, and I immediately started making an L for Lewis because my brain can't think of 2 things at the same time, is we already know that it's sulfur. We don't have to put number of protons because it's sulfur, and we could look that up if we needed to. We put down the element, and then we put in the valence electron. So the outer shell of your Bohr model with the circle and dot is what we put in. 1, 2, 3, 4, 5, 6. So the only thing we consider for the Lewis is the valence electrons, because there is where the chemistry is happening. So Lewis dot diagram is for showing chemistry of the electrons and showing their valence electrons. Good. So what I'd like you to do, this is for what I just did, which is ask you the valence electrons, but we just did that. So let's get rid of the duplicates. We have sodium there. We don't have fluorine. Do we have calcium? No. Do we have phosphorus? No. Oxygen? Yeah. Iodine? Already up there. Selenium? No. And carbon? We already have. I'm only crossing them out because they're already up there. Please do all of these and the ones here I haven't crossed out because those are different. Please do the Lewis structure for all of those atoms. think that's all of them. And I will pop back one because for anybody who wasn't here, we've got 16 protons, 16 neutrons, put it in a circle. Let's make them one. Before I forget, I posted a practice worksheet for your quiz. You can just put it away. So you have an actual paper copy. All the ones I numbered there, so the only things I crossed out were the ones that were duplicates. So essentially you're doing every single one. Lewis diagrams don't have circles. They're separate from Bohr. They just have a pairing. They're supposed to be even simpler. And okay, I can go around and take a look at how everybody's doing. On it. If you're having trouble counting valence electrons, you want to see the trick again, the mechanical and over. Ask a neighbor.
What's number 7?
Number 7 is iodine. I.
Oh, then what's number 9? That is not 9.
That's calcium. Ca.
That's an A?
Yeah, that's an A. Here, I'll prove it's an A by text recognizing it. Oh dear. I got too much. So go like this, go like that. And then and you are entirely correct, it doesn't look like an A. Now I get to be humiliated. My CA was so bad the computer thought it was a G.
I think your 9
It thinks my 9 is a Q, which at least kind of makes sense. There we go. Any other ones? I think enough people are onto it that you can start.
Is there,
Yeah,
is it, for the outer rings, is it 28816?
28818.
288.
However, I will never give you one that has more than 7. So that's like the ones that are 1, 2, 3, 1, 2, skip a few, and then they go up to 8 again. Those I'm never. going to give you one right in the middle, except maybe as a like intellectual exercise you might be able to do. You're not going to really see it on a test. Technically speaking, Science 10 pretends elements above 20 don't exist, which I think is a little limited, but
20.
yeah. They only want you up to like calcium.
Weird.
Well, they don't want you to talking about d electrons. Why is this not popping up? Is this turn off all?
Did you mark Aiden absent? Did you mark me absent?
Yes.
I'm here though.
You didn't say anything when I said your name. Did you?
Yeah.
No, I didn't hear you. I can mark you present now, but I should probably then mark you late.
Why? No, I was here earlier.
Yeah, but the house with the most lates goes last at
Oh, come
Thanksgiving.
on, don't do that.
So like that would be a net advantage for me.
But nobody likes Alice.
I won't do that.
Was here.
It's so tempting though.
I wish you liked Alice King.
This is not working. Okay. Since it's not working, and I can't do the fancy thing where I assign you a number, just remember, last time I started here, last time I started there, so now I'll start here. Nick, 1, 2, 3. The number I give you is the number you do on the board. 4, 5, 6, 7, 8, 9, 10, 11. Those of you who were spared, you can just check your work against the others. Use a different color for the dots, and I can see them.
Those who were spared.
Those who were spared.
Oh, I knew that. I did this stupid.
Up to 2 people can tap at the same time. I actually don't know where it taps out. We should check if it's 1, 2, 3, or 4.
I always thought when you see most people use it, you just represent things, and I just thought they were being lazy, and I didn't know it was
It's actually a thing, yeah.
I was like, wow, that's a lazy
It
thing.
was made by Lewis. Hold it, I think you have done something
It is
interesting.
16 valently.
No.
It is not?
No, it is not.
I checked.
What?
No. Because just before, okay, because we said that has 7, right? 1, 2, 3, 4, 5, 6, 7, right? Fluorine does. Fluorine has 7.
Okay.
Do you agree?
Yeah.
Okay. Chlorine has
7.
7. What does bromine have?
7.
7. Because we go 1, 2, skip a few. We skip the inner block. So you're doing this one.
Yeah.
So you go 1, 2, skip everything here. 3, 4, 5, 6. And that is literally part of that's like Chem 11, and it has to do with like quantum. But for our practical purposes, we can just say we just skip those. But you counted them correctly and actually made it a harder problem. Boom, 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 boom. They look good. Anybody notice any mistakes or have any questions? Excellent. Okay. There's a lot of rules on this page. I'm not going to tell them to you because if I just repeat them, you'll be really bored. However, there are 2. I'm going to do the rules, so I'm not going to explain them. We're just going to see them in an example. But there are a couple of definitions you need to know because all these rules are about atoms trying to meet the octet rule. The octet rule means that each atom wants to attain 8 electrons. We know that hydrogen is an exception. It only has 2 electrons outside of the shell. That's all it wants. And later on, you'll find there's like 1,000 exceptions. But for most of the chemistry we do on planet Earth, nitrogen, carbon, oxygen, all the like really important ones for life, they obey the octet rule. So it's still useful when we're trying to work out structures. And even the ones that are an exception, they only do it in exceptional circumstances, when they have to. Kind of like me. I only do bad things when I have to. That still makes me a good person, doesn't it? So I'm going to show you how to do the two methods. One method works really well if it has a charge, and it's like a sledgehammer. It will always work. It will carry you through a lot of things. The other method is way more visual and actually is easier to see the structure, and I really like it. I'm going to teach you both because in different circumstances, both methods are good because in the end, this is not a pipe. 2 hydrogens and an oxygen. So I write down what elements we have and how many. How many valence electrons does hydrogen have? 1. And we have 2 of them, so we have a total of, altogether, 2 electrons. How many valence electrons does oxygen have? 6. And then I always put a spot for the charge, and this just means does it have a charge? There's nothing written up here, so it doesn't have anything. But I like doing that as a habit so that we don't forget about it because it will change the number of electrons. So we have 8 electrons in total. Here are the rules. 1, put in central atom. Which is the central atom? And how would we identify it? Yes? Oxygen. You only have 1 of it. It has to be central. And then, because I've seen students go, oh, well, like, does it go like this? And the answer is no. You will not get a question in which that happens. Everything's going to dance around the center atom unless we give you something that has structure, and then we'd actually have to show it to you, communicate it in a different way. So the second one is you put the other atoms around it in, oops, I'm jumping ahead of myself, in the cardinal points. So north, south, east, west. It doesn't actually matter where as long as you put them in. So 2, put in outer atoms. And that should be outer atoms. We put them in. 3, bond, outer to inner. How many electrons are in a bond? We'll see it with the other method. It's a little bit more obvious. There is 2 electrons per bond. And now we have to account it. So this is the method I'm showing you right now is called the accounting method. I mean, it doesn't matter what you call it. But we have 2 bonds. So how many electrons is that? 4. 2 per bond. So I go 2, 4. I'll put that in brackets just so you know why. And we have 4 electrons left over. I'm doing everything in different colors so you can follow along as I do this. 4. Put electrons on outer atom until gone, or all have full shells. And I realize I've been writing fast. At any point, if I'm writing so fast, you're like, I can't keep up, you're writing this too fast. Put up your hand, slow me down. I'm also a bit panicked because I came in late. Like, yes?
What is in the equation, the bracket 2
Yeah.
ball?
2 bonds.
Oh, okay.
2 bonds. There's 2 electrons per bond, so I just want a little reminder there that those are 2. Although I like the word bob, 2 bobs. A bonding.
I read it as 2 bombs.
What does the computer say it is?
I'm not even going to try that. That you can't read either. How many minutes was I late?
Like 10 to
7, 8.
I think it was around like 9, 10.
10?
Yeah. I think you're getting old, Mr.
No, well, no, the punishment in Privet House is per minute 10 push-ups every time you're late.
I know,
Which
that's
means-
what Ellis is too.
I owe
I'm never late.
I owe the class 100 push-ups.
You can tell that I'm never late.
Okay, next one. Put electrons on the outer shells until they're gone. How many electrons does hydrogen need? When is it full? 2. Does it have 2? Yeah. I mean, it's shared, but when you share something, you also kind of have it. So it's happy. There's 2 electrons in here. So from a perspective like this, oops, hydrogen thinks it has 2 electrons. This hydrogen also is sharing 2 electrons in the bond, so it thinks it has 2. And so if they're happy, we don't have to do anything. So for this step, we didn't have to do anything. 5. Put extra electrons on central atom. Cardinal points. What I mean by that is the whole north, south, east, west. So we filled up east, west in this particular one. So I've got 4 left. So I go 1, 2, 3, 4, because that's all I have left. Minus 4 electrons, 0 electrons. We're out of electrons. We can't do anything more with the electrons. We might be able to do more with bonding, but we're going to have to check it. Six. Check if all atoms have full shell, double or triple bond, one at a time. Until they are. I am putting in the complications we don't have here. You might get into double and triple bonding. However, is oxygen happy? How many does oxygen think it has? 8. Oxygen has 2, 4, 6, 8. So oxygen is actually happy. It has its full shell, hydrogen has its full shell, and now we have water. Now, if you had come along and you'd done this, and you'd bonded it this way, that's just as acceptable. We are representing in 2 dimensions a 3-dimensional object. And that is just water rotated. This is perfectly acceptable. The other one's perfectly acceptable as long as you keep it to that. Because this is the real structure of water. If these white tops are hydrogen and these represent the lone pairs that are there, then this diagram is just this. They're actually coming out at you and those are going away. If you had drawn at 90 degrees, then you were just doing this. And so we're doing the best we can to demonstrate 3-dimensional modeling. If you go on in chemistry, we actually start doing things like this. Not erasing things. We start representing that in our drawings and going like this. To mean like, ooh, it's coming out at you, and oh, it's going away from you. And various things. But we won't worry about that. You'll see that when you do organic chemistry. Yes?
What is number 6 say?
Check if all atoms have full shell. Okay, the first part was good. But when it got to here, it went crazy land. 2 times or 3x latatone. What is that? What did those words say before? One at a time. Ooh, 1 at a time. Until they are. Good. Now I'm going to show you the other method. My board I completely filled up. I'm assuming you have some room in here that you can see the other method. So I'm just going to give myself a new page. and show you the second method. Both are equally valid. They're both useful in different circumstances. I think you'll like this one.
Which one's the sledgehammer?
The first one. We're doing it counting. We're counting our electrons. Works really well if there's charges. This works well to see the structure right away. So this is the valence shell version. So we have Lewis. So it still starts out with put in your central atom, put the other ones around it, and then just put in the valence electrons. How many valence electrons does hydrogen have? How many valence electrons does hydrogen have? One. So it just has one. This one just has one. How many does oxygen have? Six. So we go 1, 2, 3, 4, 5, 6. We're not done. Now we have to bond. So in this one, central atom, 2, bond, unpaired electrons, 3, continue bonding until octet. And this part is kind of wishy-washy. This is where the method breaks down, because you have a really difficult problem. Sometimes like you have to just know what to do, and you get a feel for it. But for ones like this, it's fantastic. So this has 2 unpairs. They each have an unpair, so they just bond. They go, okay, we need 2 electrons in that bond. We have 2 electrons in that bond, and then you rewrite it. So you go, oh, oxygen. Why so small, Mr. Buffet? Make it big. Oxygen. Unpaired. What? Unpaired. We put in those bonds. In fact, where we put them in, it'd make more sense if I did it in 90 degrees, but it's good. And we have 2 lone pairs left on oxygen, and we're done. And for simple ones, it's actually much, much faster. I really like this method. It doesn't matter which method you use. And if it doesn't have a charge, it's probably this method that's going to be fastest. If it has a charge, the other method will probably stop you from going down a wrong path. Also, this shouldn't be touching. It's a bond, not a friend. Good. Questions? Bond? So, let's see if the thing is working again. I'm sure the network has been working for you completely wonderfully.
No.
Yeah. Okay, never mind. Give up on that. Grab a partner. However, the only caveat is it can't be the same partner from last time. Grab a different partner. Erase work on the board. Do that problem any method you like.
Yay!
And I'm going to start my 100 push-ups.
Yeah, Mr. Bell.
Yeah, you know the last time I did push-ups?
Last year?
Good.
He wasn't at the start.
I'm only going to do 10 at a time. I'll eventually get through the 100.
Hey, he didn't start on him, so he was doing it.
Okay. You're still writing. I could probably do another 100. 10. Once you think you got yours, have a seat.
We're supposed to just do the same thing as we did for the water, right?
Pardon? Just same thing. Either method.
So that means. I wasn't writing.
Were you with the group? Is that your answer or is that your work?
A little wall push-up. I know, it's short. He's still up there.
It's just for charge. You're going to find that you're going to get examples that aren't H12, but they're NH4 plus 1. So if you have a positive charge, what does that do to the work? Yeah, well, you take one away. So that allows you to take one away. Those are looking really good.
Chemistry. When is Thanksgiving?
Why do you celebrate Thanksgiving?
Are you looking for your cat, Nick?
Celebrate.
Me and my lick your mustache roll.
Okay. Everybody seemed to be doing quite well. You got the right structure right away. Accounting method, someone did the counting method, looks perfect. You minus the 8, that's awesome. If you're doing this method, you just went to the final structure, so you might have seen it in your head, but you would do that, you'd see that they all match. Notice to set myself up, I start putting the valence electrons towards the central atom if they're on outer atoms, because then they show it. And then you end up with, as everybody did, this one. Now, this can get a little bulky. So a lot of students who do this like doing this. They just attach them. You can see that structure a little bit easier. However, don't leave this as your final structure. Redraw it, because a dot, dot, and a line actually means 4 electrons, because there's 2 in the bond and 1 at each end. And they're not necessarily positioned quite right. You want to redraw it nice and neat. Not that now that I look at it, this particular version is nice and neat. Recognize the shape. What does that do? That's terrible. The nice and neat version with proper bonds. Excellent. Okay. What kind of compound is this? Yes.
What is the positive, like when you're adding together all the electrons, what is the positive?
This?
Yeah, like what
This is
the-
for charge. So I'm going to jump ahead. Did we do it yet? There. So I'll just start this one, even though we're not going to do it right. I'll start it. So if we were to do this one, we would say, oh, there's nitrogen, there's hydrogen, and there's 4 of them. And for the plus minus, we have a +1 charge. What are the valence electrons in nitrogen? 5. And in 4 hydrogens? 4. And if you have a +1 charge, did you gain an electron or did you lose an electron? You lost one. So for every +1 charge, I change the sign and I make it opposite to show that we lost one. So instead of 9 electrons, we actually only have 8 electrons. So this is just to remind me to check the charge and put that in there. Does that make sense? Back to this one. What kind of compound is H2O? Yes?
What? Isn't it ionic?
No.
Oh, it's covalent.
It's covalent. How do you know it's covalent?
Because they're non-metals.
They're nonmetals. And what about methane? What kind of compound is that?
Also,
Yeah.
Is it an ion?
Hmm? Nope.
Polyatomic.
Nope. Well, no, actually. I mean, it is a polyatom, but it's polyatomic ions have a charge. We call it a molecule, though. Is this a metal?
no.
No. So, nonmetals usually mean covalent. What I haven't shown you is what we do for ion. Hold it. What kind is this? It's ionic. This is ionic. How do we know?
Because sodium's a metal.
Sodium's a metal. Now, metals are usually, it's a metal and a non-metal. However, can anybody, for bonus points, name me an ionic compound that is entirely made of non-metals? Possible. It's a little tricky in that, and
Carbon 2 sulfur.
carbon, no, that would be non-metal. Carbon's a non-metal. Fully non-metal. The trick is that you use this. NH4, that's +1, could be paired up with, say, chlorine, and you have ammonium chloride. You have a positive thing and a negative thing. So you have an ionic bond bonded to, this is covalent, so it's all nonmetals, but it has a charge, so it can bond ionically. So I just wanted to put that here as a reminder. Ionic means positive attracted to negative. It doesn't mean metal and nonmetal. It's just that's almost always the case because metals become positive and nonmetals become negative. But there's lots of exceptions. And ammonium is probably the most common one you'll see this year. By the way, that's only true for ions. Opposites do not attract in like real life, just in chemistry and rom-coms. Okay, I want to show you how because we do Lewis dot diagrams a little differently than we do them with covalence. So I'd like you to draw the Lewis dot diagram for sodium and the Lewis dot diagram for chloride, just separately, individual atoms there.
Who is this Lewis fella?
Yeah, let's find them.
You know leotards are named after a guy?
Really?
Yeah.
I did not know that.
I don't know why anyone's saying this thing.
Don't ask how my brain works. Because I don't
Brain
know.
works, mine doesn't.
Oh, wait.
Everybody's brains work.
What if your brain dead?
Exactly.
Well, then you're dead.
But then your brain doesn't work.
Yeah.
Technically speaking, if you're brain dead, your brain's still working. You're just not
Not
cognitively
properly.
thinking.
No.
Because your heart's still beating, although you don't really need your brain for your heart.
Your brain's
But if your
dead.
lungs are moving, your brain's still working in some capacity.
What if your lungs aren't moving?
Then it might be
Yeah.
your brain's gone. And then it's probably some machine forcing it in some sort of weird, you know,
Post-apocalyptic future.
yeah.
Why did they? Why
No weird questions right now. We're doing this. I was late. We need to get back on task. For the first one, how many valence electrons and where would we put it? Miyabi. 1. And for the second one, Aiden.
7.
7. How did you put it around? How many where?
1, 2, 3, 4, 5, 6, 7. So 2 on the top.
2 on the
2
top.
side. 2 on the bottom. And then 2 on that side.
Perfect. So this is how they are individually. For a covalent compound, in fact, just to, for an ionic compound, just to illustrate the point, I'm going to make it a different color. So my apologies if you copied me. There we go. is that this is an ionic bond. What do the electrons do in ionic bonds? Pardon?
They like, yeah, they merge.
They merge?
Yeah, the anion and the cation.
The anion and the cation, well, they are attracted, but I think covalent, if I'm understanding it, would be more of a merging because they're sharing. What does sodium do with its electron? Yeah, it gives it. So you just literally show that. You go. Now, since you can't on your piece of paper go, I'm going to redraw it. But then the final one is that. And then the only thing we have to do is show the charge. We have to put square brackets around to indicate it is the entire thing. Oh, and I should have asked someone the charge. However, I've asked someone chlorine or chloride. What is the charge on chloride with an extra electron? No, you already asked. Yep. -1. And then you're done. So there's no bonds in ionic compounds. You just move the electrons around, and then you, if they're charged, you put the charge in. If it was sodium oxide, you'd end up moving 2 electrons, and you'd have 2 sodiums and 1 oxygen, just to fill its shell. Salty?
Sodium chloride.
Oh yeah, that is very salty. Tasty. A metal that explodes upon contact with water, and a poisonous gas that is the base ingredients in mustard gas, makes really, really tasty French fries. Now, whichever method you use, keep in mind the famous pipe. What does that say? Louder?
This is not a pipe.
This is not a pipe. Je ne parle pas français, so I always need someone to translate. This is a very, very famous painting, and it's called I believe it's called The Treachery of Images. Is that a pipe?
No.
No. What is it?
No, it's a pipe.
Pardon?
A pipe.
A pipe. Is it a pipe?
Yeah.
Can you smoke it? No, it's not a pipe. It looks like one, but is it one?
It's a depiction of
It's a painting of one. Is that a painting of a pipe? No. It is an image, a copy of a painting of a pipe. There's no texture marks that we can go in and touch. It's just a fake. So is that a picture of a painting of a pipe?
Yeah.
No, it is an LED projection of a picture of a painting of a pipe. And this is one of the perfect illustrations, I think, of all science. I have shown you 2 different methods to make Lewis dot diagrams. And Lewis dot diagrams are themselves an abstract representation of a Bohr diagram, which is itself an abstract representation of what's going on in an atom. None of them are true. They're just useful. So if you want to explain a pipe to someone, that's useful, but it's not actually a pipe. Lewis dot diagrams aren't the atoms. DNA is not a blueprint. It's also not a recipe. It's something completely different. All these are just mechanisms to understand something. So if the mechanism isn't working, that's why we have more than one method. They're both kind of wrong. They're just different in the utility. So don't confuse what it actually is to what we're doing. Anyway, do HCl, then do F2, then do NH4 plus 1, then do CO2, then do N2, then do NO3 minus 1. And at some point, I'll start heading you to the board to do them. Maybe assign them to like groups. So just start at the first one and go.
Are you just doing the Lewis model?
Pardon?
Are you just doing the Lewis model?
You are making the Lewis diagram of these compounds. Yep.
Chlorine.
Yep. And they start easy, but there's going to be some twists as you go.
I didn't like how you said twist. What do you mean by that?
Twists. Fun little things that are lie and surprise.
It's just hydrogen chloride. That sounds like something that'd be in a bomb.
Did you say hydrogen chloride? Sounds like someone who'd be in a mob.
Sounds like something that would be in a bomb.
In a what?
Bomb.
Bomb. That'd be a really bad bomb.
Oh.
It would spray hydrochloric acid all over you, so you'd also start melting.
See?
Oh.
Fun.
Yeah.
It could go in a bomb.
Yeah.
What if it melts?
It goes
into
in a water gun.
Oh.
That would literally be in, chemical warfare. We're now using chemicals to like burn and poison people. A lot of that's been outlawed.
You think I'd get arrested if I put it in a water gun
Yeah.
and start spraying it?
That happened in the 60s.
What?
Men,
Of course.
we would call them today incels, put concentrated sulfuric acid in water guns and would run around the streets of London and spray women in the face. It was like a whole little, its own little terrorist thing for a while.
Oh,
Yeah, it was an actual thing.
that's
Charming.
nice.
Yeah, very charming.
Do you have any good
I'm
stories?
glad that stopped. Pardon?
Do you have any good stories?
Good stories.
As in stories.
I do. Good stories.
Mr.
While you're working, I'm going to call it up because we need the odd good story.
Mr. Newfield, I have a question.
Yep, that's a possessor statement, and you do have one.
May you answer my question?
I'll come around.
Can you answer? Or may you? It's can you.
I'll come around. I want you to struggle with it. Ask your partner.
What do you do after this one? Oh yeah.
I think that's what you're supposed to do.
Owen, have you ever played Minecraft?
Yes.
Why is the network
Why?
so? Never
Just
mind.
curious.
They're working as hard as they can. I should not complain.
I like how the school spent money on desks that can go up and down by the learning commons on the wall, but not on their.
We didn't spend money on that because those were pre-existing, so we just moved them.
Oh,
Yeah,
Didn't know that.
they're in the old building.
Why are you using DuckDuckGo?
that's.
Because I don't actually. If you want to use Google, use and UDM equals 14.
Yeah. It's better.
And UDM 14 if you want to. And someone actually made a helpful website for it called udm14.com, which automatically does that to your Google search. It pulls out all the pablum, all the AI generated stuff. So it's still good.
It doesn't use it.
Google, but you can say, and it gives you results like it was 5 years ago, and they're usually much, much better, so they don't have all this AI generated stuff that's just repeating things for clicks.
It's from
I love
2011.
the ozone layer. That's a great story. Makes me feel better about the
Ozone hole update?
extinction.
I just wanted, I want someone that has like an animated GIF. Because it's one of our great positive stories, if someone wanted a positive story.
Yeah, we don't get
It's-
a lot of those things.
Okay,
us.
okay, accept all cookies, I don't care, give me all the cookies. All the cookies. Ooh,
Oh, okay.
video. Oh, better shut this down. Yeah.
Can't get copyrighted.
The ozone layer was responsible for, it's O3 instead of O2. It's made naturally in our atmosphere by extrasolar radiation. It's solar radiation. And we ended up with a huge hole in our ozone layer. because of chlorofluorocarbons. Chlorofluorocarbons are normally what we thought a very inert gas. They're carbon attached to chlorine and fluorine. They don't react very much, so it's like methane, CH4, but like C with 2 chlorines and 2 fluorines. And I don't know if you've ever seen pictures of the 70s, but people had like big hair and lots of hairspray.
Yeah.
The hairspray was filled with this as an inert gas that they could use, and then they could pump out all the hairspray at high speed, and people were doing that. It was also used in industry in a ton of places. Your fridges actually still run on versions of these. However, we noticed it was going. We found out that those CFCs would go up in our atmosphere and they catalyzed the breakdown of our ozone.
It's a pretty big hole.
So they weren't reacting, but they were causing the ozone to disappear. And they stayed in the atmosphere for a long time. So the whole world got together in Montreal, and this became the Montreal Protocol, and said, we're not going to do this anymore. And they all agreed we're going to stop. We put rules on how much CFCs you can do. We're going to take it out of a bunch of things. It's not going to be in hairspray anymore. Very, very lately, it was looking like it was getting bigger again. And now it's back on track to smaller. We actually pretty much made it almost completely disappear, but it's not quite gone yet. Australia was actually having its rates of skin cancer skyrocket because of the whole ozone layer, because more of the UV rays were getting through. We found out through satellites that there's a number of factories over the world. There's quite a few in China that were releasing these CFCs, and we're just like, hey, China, and the government was like, and stopped them because they're just as worried as anybody else, and the factories were doing things illegally, so that we can check on it and make sure the whole world's in agreement. And the whole world just basically got together and said, yeah, this is a big problem, and we're going to fix it. So we have big problems. As long as you can get everybody to agree, like, we can definitely fix them. We just need everybody to decide that we need to fix them. Polio was almost completely eradicated like smallpox was, because we had nearly everybody in the world vaccinated against it. But then that stupid doctor faked a report and basically pretended that vaccines were linked to autism. A lot of people got worried, and then vaccines slowed down, and we didn't quite eradicate it. Now that that's slowly going away and people are getting a little bit more educated, again, hopefully we can do that. We completely eradicated smallpox worldwide, a really deadly disease for which there is no cure. Once you have it, you are gone. Not 100% fatal, but it has very bad effects, and it is often fatal. We vaccinated everybody on the planet, and now smallpox doesn't exist.
There's
It's
two.
just gone.
There's a lab in Russia and a
Yeah,
lab in the US.
it exists in a lab.
I feel like that's just like, in case we need it.
Well, one worry is
Purposes.
biological warfare. The second worry is, what if you were like, I don't know, digging in the Arctic and you pulled up a sample from 1,000 years ago, which turns out had smallpox spores, and it came out again. Samples help us make a vaccine fast. So there's also good reasons to keep little bits around. But yeah, you also want to trust the people that have it. I don't know if I
I
trust
say
the people that have it, but yeah.
Send all the smallpox to Switzerland.
4,
I
5,
trust Switzerland with smallpox.
7, and 8.
They're neutral.
I do trust Switzerland. It's not, no, don't trust me. Why is it so slow? So slow. It's so slow. 3, 4, 5. Okay, fine. Forget it. Stupid. Not going to wait for you again. 3, 4. How many do we have? 3, 4, 5, 6, 7, 8. Remember your number. What do we? 3, 4, 5. Remember your number. 6, 7, 8. 3, 4, 5, 6, 7, 8. 3, 4, 5, 6. Get your grip, go on the board, do that problem. Erase what's already there. On the board. last 5 minutes of class or so. This ends at 35, right? Erase what you got. I need to consistently start. Pardon? Yeah, Lewis models for the compound. Nope, it's F2. And you need the valence electrons on each F. How many valence electrons are on the fluorine? Grab your periodic table. Are you in the same group?
Yeah.
Grab your periodic table. It'd be helpful.
I think I got it. I think I got it 4. Yeah. I think I got it.
Marker. Yo, I need another marker. How are we doing?
I want to see a method with it though. Like
Okay, I
either
did.
method. Show the
I did
joining
it
up
on
of
the
electrons
thingy.
or
I
the
did it on the
accounting.
thingy.
Either one. All good.
Yeah, that's the one, right?
Nice to meet you. Confused. Mr. Neufeld. How many electrons are in fluorine?
Well, I know the valence electron is 7.
Yeah, there you go.
But then there's what's the
There's 2 fluorines. Yeah, so you need F and F.
So I do F.
Yep. And which method are you going to use?
Lewis.
One.
Oh, yeah, just put the Lewis around them. I think it'll pop out as soon as you do that.
That's happy, right? So 1, 8. This has 1, 2, 1, 2, 1, 2, 1, 2. There you go. I just calculated that.
Hold it.
That's right. Is it not right?
How many valence electrons does nitrogen have?
Is that it? Sneak up?
7 or 8.
I think your instinct was dead on, so the answer's right.
No, because I did it on my paper.
Well, bring your paper here. Yeah?
Is that correct?
Sounds good. Yeah.
It's probably different.
I don't know. It was
But you
confusing
can,
me.
you
It makes
also,
sense now.
how many
Call
valence
7.
electrons does did either of you bring your periodic table? Sadly,
It has.
do you know that for years I carried a mini periodic table? It's so important. You should carry a mini periodic table in your wallet.
It goes right now. With our both those.
Which
Are you getting knocked down?
But in your bag, you had a mini periodic table.
Okay, I figured it out. So basically, it's plus 1, 2, 3 electron. It would have
Dude.
9, and then but then now it has 8. So then the N has 8 because the two lines
Yeah.
have 2.
Okay.
And all the H's have 2. So
Yeah, what you did is the accounting method, but just totally different. What I wanted to, number of valence electrons, is just to make sure if anybody was looking at these, hydrogen has 1 each. And you go 3, 4, like that. But the important point is to get rid of one, right? So you just go like that. And now you can see they all hook up, and you get the same thing. Yeah. How was that? Good. Okay.
I just, when people talk about solving patterns, I just think about weird fan fiction.
Okay. I'm gonna go through. Look this way.
Tells me more
Wait.
stories about what they've read on
Wait, wait.
Well, that worked reasonably well. Okay. Looks good. Good. We see the thing. It's helpful if you're drawing these on the board. Put all the ones down. That helps other people see it as well. There's 4 of them. Show the 4, and that shows the bonding. But you're right. This one bond. It went between the 2. So you ended up with that and that. I'm just showing the work. Nothing wrong with that. That's from before. Another good one. We did the accounting method. 8 electrons. Put the bond there around the other atom. Perfect. Is nitrogen happy in this one? nitrogen is incredibly unhappy. Nitrogen is unhappy because how many electrons does this nitrogen think it has? How many electrons are in the bond? 5, 6, 2. How many electrons in any bond? 1. No, 2. See, I'm not, see this, I came late to class, I can't count. 2. How many electrons here? 3. And they're all unpaired. This is incredibly reactive. This will not work. So we have 2, 3, 4, 5. How many does nitrogen want? In total, just how many does any atom want? 8. Octet rule. So when I said you join unpaired electrons, you can keep joining them. You can go. Then you get nitrogen with 2 bonds. Like that. Now hold it. Nitrogen is 5. 1, I think there's something wrong. Actually, 1, 2, 3, 4, 5, 6, 7. This doesn't have the right number of electrons to begin with. How many electrons do we have? The group that was up here, you did this part good, and it looked really good, but when you went to here, you actually gave up before you finished the number of electrons. So this is 2. That's the bond. By the way, those were much easier. This is the first one with double bonds, so it's not a criticism in any way, because this is the tricky one. And then you put 8, and you put them on the outer atom. You spread them out. But you can do that as well, and I'll go with what you did, because it will still work. But you have to use up all 8. So you go 1, 2, 3, 4, 5, 6, 7, 8. Or you can put it there, doesn't really matter. Or do that, make it even. So now we have all 10. Before you go, is this one happy? How many electrons does this nitrogen think it has? 2, 3, 4, 5, 6. But if we did this, join 2 up, now it thinks it has 2, 4, 6, 7. Do that again. 2, 4, 6, 8, and we eventually get there. You can double and triple bond to increase the number of electrons it has through sharing, because chemistry at its foundation is communist. Sees the means production in the next class. Work on that for homework. You have your quiz worksheet as well. Work on this just for maybe 5, 6 minutes. See if you can play around with the other ones, and we'll continue it next day. Look over the worksheet. I will post the answers to the worksheet, and your quiz will be based on it.
If there's only 1 electron that's going back in time, why is the missing enough electrons to fill all the really cells normally?
We don't. Why isn't enough valence shells to fill it normally?
Well, like, they need to share.
Yeah.
Why isn't there just enough electrons to fill all the shells without needing to
There's-
share or swap?
When you create the universe, that asks the question, why isn't there like too many? Like, why isn't there like 1,000 electrons for every proton? Why is there almost enough? Or is there 1 electron for every proton? And they're sharing because other ones have stolen it to get full shells. Oh, I have to think about that.
Now, why couldn't you
Yeah, this is a problem with the whole thing. Sorry, yes.
Can I go to?
You want the same thing?
You got first here? And something.
You went to first class? And it didn't work? Okay, let me just stop this from recording.